It is my immense pleasure and my honor to welcome all of you here, all the dignitaries who have come far away, especially to make this event a very successful.
At this time, I have the distinct pleasure of introducing you to our very first eminent speaker. Nagendra Prasad is a highly experienced technology consultant with nearly 30 years of expertise in development and testing. His career spans global organizations where he led product development in embedded systems, covering mobile devices, in-vehicle infotainment, and cellular base stations, specializing in automated testing for over 11 years. Nagendra Prasad will share his research and specialize in validation and test automation, infotainment, instrument cluster, and ADAS ecosystems. Welcome him to the stage. Thank you.
Thank you very much. Good morning, everyone here. It's a real privilege to be part of this event here. Thanks for the opportunity. Today, I'll be talking about my expertise and experience in automotive electronics and validation and test automation. So, the agenda I plan to cover is that my area of expertise is validation and test automation. Validation means that testing of a system we developed, whatever it is, electronics, hardware, and software. So, the idea is that we'll cover the different electronic control units which are part of the automotive systems and the challenges involved in testing and automating them. The main focus areas, if you look at any vehicle, right, these days it's more like a enterprise solution itself because there are independent electronic control units and about 40 to 100 based on the type of car and based on the feature set. So we'll talk about the activities involved in the development cycle, the testing, the automation challenges. We'll focus on three key electronic control units: infotainment system, instrument cluster, and ADAS systems. So, to give a quick overview of what a automotive industry looks like from an ecosystem perspective, they are divided as tier 1 and OEMs. Tier 1 means they are the suppliers. Basically, whatever the electronics being built, the braking control, the emergency braking, the seat belts, or a parking assistance. These are independent ECUs, electronic control units. These are supplied by tier 1 companies. Tier 1 means Panasonic, Harman, Denso, Continental. These are the tier 1s. The OEMs, the original equipment manufacturers, are the car manufacturer itself, like the Honda, BMW, Audi, Ferrari, Porsche. These are the OEMs. So my expertise is working with tier 1 and OEMs, where tier 1s are the electronics unit suppliers. OEM are more like the integration. They are the integrators. They bring in all these components from the suppliers, build a product, build a vehicle, and release it to the market. So that's a quick overview of how the ecosystem in automotive world lies today. To give a quick overview of, we talked about different entities in the automotive electronics, right? If you broadly categorize them, you could say that they fall into the safety category, where you have emergency braking, AEB, it's called automatic emergency braking, or a BLIS, which is a blind spot information system, or a adaptive cruise control. These are all the safety features. There is something called as comfort and convenience, be it your seats, be it your cabin theme, be it your the heat setting of your seats, etc. Then there's the battery management system, the convenience and comfort, and the power electronics itself. So all these compose, and if you just look at it, right, the number of electronic control units are multifaceted. Like there's something called a tire pressure monitoring system. There's something called lane departure warning. And why the validation and the automation challenges are intense is because the expectation is that these electronics, these equipment are supposed to operate between minus 40 degrees to plus 125 degrees. Because these vehicles goes across the world where the geographies are different, the weather is different, the demands are different, the ecosystem is different. So we have to make sure that it works perfectly fine, because the risk involved in a fatality, if an electronic component fails, the risk is very high. Though the today's statistics says that the number of accidents, 95% are due to human error, the machinery failure is less than 5%, but still we have to make sure that that 5% is covered well and we don't get into any risks. In automotive, there's something called as automotive safety integrity level. It's called ASIL, and the levels are A to D, level A to D, A being the lowest and D being the highest. Suppose there is an electronic control unit which is categorized as ASIL level D, and there's no possibility or there's no scope for error at all. For example, an automatic emergency braking cannot fail at all, because any failure there is fatal to the passenger and the driver, whoever is part of the vehicle system. So the lowest could be something like A, where the risk assessment itself is based on the severity, the frequency of occurrence, and the controllability itself. So these three parameters form the rating, which is the AC level A to D. And I'll talk more about the AC level D. This is just a quick overview of how the automotive electronics, I was saying, right, it's more, if you look at it, it's more like a complex network by itself. So each one is an electronic control unit over there, and they talk to each other like our networking system. Assume that you have like 50 computers talking to each other, and they have to be well coordinated, well synchronized, and completely updated with what's happening on the other side of the ECU. So that's overview of this. And the reason I brought it up is the technology is evolving such that they want to move away from this highly complex network to more a zonal based network. So going forward, the vehicles will be divided as zones, as 4 zones, the first 2 zones in the front, second 2 zones in the second, and the feature set will be divided across this, so that the communication and the complexity of dependencies are brought down to a level. And these are different protocols followed in the automotive world. There's something called CAN, Controller Area Network. This was introduced by Bosch in the 1980s. They were using it to talk to between 2 ECUs. Now it has become a standard, and all the automotive companies follow that. But going forward, the demand for traffic is very high. The amount of traffic, internet traffic, which talks, yesterday we were talking about connected vehicles, right? Going forward, all the vehicles will have a direct connection to the network. A lot of computing happens on the cloud. So basically what happens is that you need more and more of bandwidth to talk to the backend cloud. So the vehicle network is also moving to something called the automotive internet, Ethernet. We have the regular Ethernet. We know that in any enterprise, any company, any institute, any school, college, we have Ethernet communication, where it's a communication between 2 PCs or host machines. Same thing is being extended to automotive world, but there the noise levels are very high because of the electronics involved, because of the RF emissions, etc. So there we bring in automotive Ethernet. That's a new standard being evolved. I'll give a quick overview of what an infotainment system is. Of course, all of us have been using infotainment. As you get into your car, the immediate thing you do is you switch on your Bluetooth, you pair with your car, you start talking to anybody over the phone using the car as a medium. So this is called infotainment. Infotainment is a portmanteau. It's 2 words combined. Like we say motel, right? Motor vehicle hotel, or brunch, breakfast, lunch. So infotainment is information plus entertainment. So earlier it was more like entertainment, now it's a lot more information. This quick evolution of how the infotainment world has come through over decades. In the 1930s, early 1950s, we just had a radio tuner. You could just tune it to a few channels, and listen to your favorite music or maybe weather, news, etc. What happened is that there was a need where lot and lot more information was supposed to be exchanged and shared with the vehicle passengers. So later they brought in a entertainment aspect to that, where we had the audio cassettes, you could play back audio. Then came the CD. Later it evolved to a USB drive where you could have your favorite songs being put into a USB drive and play back. And as the technology evolved, we also have the phones came into picture. So the phone world, the mobile world and automobile world came into a convergence where you could do a lot of things from mobile onto the infotainment system which is in the car. There are two technologies which came up called as mirror link and miracast, where you could mirror your phone on the infotainment screen. So those technologies survived for a few years. Then came Google, where they brought in something called as Android Auto. Android Auto is you can have all the features or at least limited set of features of your phone on the infotainment system. Your calling, media playback, your texting, and some of the applications like your Spotify or Microsoft Teams, all that are now possible to get extended onto your infotainment screen. Since Google came, Apple can't stop anyway. So they came up with something called CarPlay. So that's an equivalent technology for iPhones, where Android Auto is for Google phones, Android platform, and CarPlay is for Apple devices. So this is a quick evolution of infotainment world, how it is today. So today it's seamless. As you get into your car, the latest technology is something called as phone as your key. It's called POK. So you don't even have to have a physical key. Once you have your phone, all the authentication is on the phone. You could just walk in, get an access to your car, and move on. We are talking about connected vehicles going forward. What it means is that in a few years from now, if not for COVID, we would have probably had robotaxis by now. Tesla was planning to release robotaxi by 2020 and 2021. Unfortunately, COVID hit us and everything stalled for a few years. So vehicles are moving to something called as autonomy mode. It's called autonomous vehicles. So even in autonomous vehicles, there are level 0 to 5. Level 0 means the very traditional conventional vehicle where we have our steering wheels, pedals, the driver manages the driving and everything. Level 5 is completely autonomous to the extent that there is no pedals, no steering wheel. So there is no intervention possible by any driver who wants to take control of the vehicle. So this is ADAS is advanced driver assistance, where there are some basic features like you can try to do a parking aid, you can get a parking assistant, you can do a automatic emergency braking, blind spot information system, and traffic sign recognition, all that stuff. For example, when you're driving through a road, if there's a traffic sign recognition which says that 50 miles or 50 kilometers is the limit, the vehicle can read through its sensors. Sensors are camera, radar, lidar, ultrasonic sensor. It reads the traffic sign pattern, automatically controls the vehicle speed. Suppose it's a school zone, there's no chance, we don't take a risk, the vehicle automatically takes control. That is the autonomous levels maturing from 0 to 5. Level 5 means it's completely autonomous, no intervention possible. It's as good as like we sit in a conference room, face each other and keep talking, and it delivers us to our destination. Tesla is planning to do that in a couple of years now. So since the feature is so complex and the risk to be taken, these all fall in the SA level D, which means that the risk is very high, the fatality could be very high, and it has to be a thorough testing in the labs. And just to give an example, if you have to test such a car on the road itself, looking at all the possibilities, children coming in or some other unknown traffic coming in front of you, to do all this, it may take at least like 40, 50 years to test a vehicle on the road, which is not practical at all. Because if you have to release a vehicle, typically we release cars in 2 to 3 years time frame. If this is not the case, if you don't have a equivalent test automation environment in our lab setup, it's very difficult. So there's a concept called as digital twin, which means to say that whatever you see on the road, for example, we drive to this road, we see this new college, then we get into a square, then we see a restaurant. So all this is mapped as digitized in the digitized world. In the lab, we get the same environment and simulate the vehicle condition. What we do is we play back the video, like the camera sensors on the vehicle will be focused towards the screen here, and it's a drive route here. So the a vehicle actually thinks that it's actually driving through this Holywell Street, and it knows that there's Imperial College on the left, new college on the left. There's a restaurant called King Sam on the right. So it knows what is the possible traffic. It manages the whole thing. So digital twin. So my specialization is in this area where we try to bring in the environment of the real world and try to test it in the lab. So the complexities are very high because you have to. I've given a few examples. For example, during the Halloween times, people are dressed like pumpkins, etc. Right? So car should understand whether it's a real human or is it some doll there. So accordingly, it has to act. But unfortunately, during this testing, there have been accidents as well. As recent as 3 months back, unfortunately, there was a death because the vehicle could not follow or understand that there was a pedestrian who walked in between. So the testing challenges are very high. The automation needs are very high. So that's my area of expertise where we trying to bring in the whole environment of the real world into a lab and try to mimic that for a vehicle to be tested. Next couple of slides talk about the different methods of testing. Okay, I'll introduce you to a few terms so that it will be helpful for future reference. There's something called a smoke test. Smoke typically is that you switch on something and if it doesn't burn down, it's a smoke test. But the etymology is interesting. The smoke test actually comes from the olden days where they were like in New York, where they were laying the pipelines, plumbing work in hotels or big buildings. They used to seal all the points and introduce smoke. So if there's no leakage anywhere, then they say that the basic thing is working. So probably that's one of the reasons, one of the etymologies where the smoke test is derived from. So every time we do a testing of a system software, there is smoke test, there is integration testing, there is system testing. We do a stress testing, load testing. Stress testing means that suppose when you are in car, the extreme case is that the car is not supposed to fail in as much as possible. Suppose as an extreme case, you have a media device, you loaded 10,000 songs and just stick it into the car. It should not get stuck because 10,000 is a large number. Just to index it will take a lot of time. So we do all this testing in the lab. It's called a stress testing and load testing. So you're doing a navigation and you're continuously changing the route. There's a continuous stress on the system to reroute your path to your destination. So these are the kind of things where we do. It's called basic sanity smoke testing, integration testing, load testing, stress testing. So these are the different methodologies we use in our testing. As an extended thing, one other important point I want to bring is that when you build a complex system, complex software, the dependency on features are very high. For example, you have a Bluetooth, you have a camera, you have phone. So basically what happens is you want to take a picture, send it to somebody or Bluetooth. So it means to say that the camera feature and the Bluetooth feature are tightly coupled. So if something goes wrong in Bluetooth, your camera feature, some of it may get blocked. Okay, so that's kind of, it's called integration testing. So we have talked about smoke testing, integration testing, system testing, stress testing, load testing. So next one. This is just the way how it works. Typically what we do is once the software is available in a day's time, we build it, test it, give the results, whether a go or a no-go. Yeah. And automation is key, as I said. There are multiple ways of doing the test automation. One of them is called camera based, which is non-intrusive. You have you place a camera like this and it tries to capture the behavior of the device on the screen and verify it based on the image recognition, optical character recognition, like that. So that's different types of testing. Yeah, and in our automation, test automation, basically we have to mimic everything. For example, you have a voice command, right? So what we do is there's something called text to speech and speech to text. So basically if you type in as hello, good morning, it reads out as hello, good morning and plays back in the car and checks out if it can recognize or not. Similarly, if there is a playback there, capture it and then verify the text. Yeah, we'll go ahead. So this is one of the areas where I have a patent. I have a US patent in test automation area that was done about when the initial days of technology was evolving. It's in the media testing. I think that's a quick overview of what we do in test automation in automotive world. Thank you very much. I'd be happy to discuss any points, any questions you have.
And I just wondered, in the future, I'm sure it's not there now, but with automatic driving, I know that's not the correct term, but with automatic driving, Could it be programmed in the future to do high-speed pursuit driving?
That's an interesting point. I never thought about it, but that's a possibility because these police vehicles and the service vehicles are much more capable than the normal passenger vehicles. Even speed wise, they have a higher power, they have a higher engine power. So that's a good thing. I know so far I've done all the use cases. This was never in the picture. We do military was a situation where it's covered, domestic and delivery, and in a highly risky area like a chemical world, it's there. But this is an interesting point.
It just occurs to me looking
Yeah.
at the differences between
Correct.
commercial to military
Correct.
temperatures, and I thought, well, what is higher electric?
Yeah.
I wonder if it could be a higher grade program.
Right, right. That's a very interesting proposition. I'll consider it when I speak next time. Yeah, sure. Thank you very much. Thanks for your time.
The next one goes to Dr. Nagendra Prasad.
The last 3 days has been really interesting. It was a good opportunity to meet researchers across the globe. So the learning, the knowledge sharing has been very interesting. And we got to meet people across the globe with different cultures, different area of work. So overall, it has been a wonderful experience.